Hi everyone, 10 o'clock, and we'll get started on our first talk of the day. So we'll be writing an I2C sensor driver with Colin Dietrich. His pronouns are he and him. Colin is a data scientist for a cloud services company. He used to help organize Puget Sound puppy meetups. I think that's called Puppy, and which include hardware nights. And during that time, he collaborated with several members to create the, if I'm pronouncing this correctly, Duwamish Lighthouse project, which they presented at a meetup. He started writing drivers for MicroPython after the Lighthouse while working in oceanography. The driver presented is part of his hobby project to build tools for some of his scientific work while demonstrating a way of generating data on device that streamlines ETL and analysts. I'd like to also add, Colin's available for Q&A in Venulous and in person, so I'm looking forward to seeing all of his questions that come up during his talk. Please join me in a round warm applause for Colin.
I'm Colin, and I am going to be talking about writing an I2C sensor driver. And I am not an electrical engineer, so apologies to any electrical engineers in the room. I am self-taught, and I'm more interested in data analysis than I am all of the hardware. I'm definitely a MicroPython enthusiast, and I was once invited to a data formatting cage match, which I did not win, but that is what brought me to this work, was thinking about how data formatting and the way we collect data matters to the downstream users of those data products. So what is I2C? It stands for Integrated Circuit. Some people pronounce it I2C. I often say I2C. It's sometimes written I2C. It was created in 1982 by Philips, which is now NXP. And it's used by many manufacturers for on-device communications between chips. Compared to other technologies, it's relatively slow. It's not suitable for long distances, so like running through the room would be impossible with it. But it requires very few connectors, and it's used in everything. It's in your phone, it's in your computers, it's in your PC at home, and it is on the podium here on a small microcontroller. So what are we going to do? Why are we doing this? This is going to be a bit of a crash course in hardware. I'm going to try and keep it a shallow dive. Like I said, I'm not an electrical engineer. I have some opinionated data scientist sort of output that we will get to, and then some next steps that hopefully at the end of this, anybody interested, if you want to write a driver for some device, you'll know where to start. So MicroPython, let's just quickly go through that, I kind of think of it as a REPL for the real world. It is a compiled Python interpreter that runs on a single-threaded microcontroller. An advantage for deploying instrumentation and analyzing data is that you could write the same code in pure Python, put it in your controller, and also use it in post-processing and know that the exact same code produced your final results. MicroPython has really easy JSON support, and for a lot of tasks you don't need the compiled, optimized output that more industry standard tool chains provide. So it's good enough, especially for first round prototyping, where the REPL really rapidly helps you narrow down, like there's something wrong on the bench over here, and I don't have to wait 3 minutes for every little adjustment. Why write a driver? Partially to include more information to the end users. If I just get a file with a bunch of integers in it, it doesn't tell me a whole lot about what's in there. And also, I'm interested in a little bit more cross-platform use. I don't like redoing my work. And then I2C, I already alluded to the fact that it's low cost. Also, the makers, different companies have actually started standardizing these connectors. So the couple that I have here, they've kind of standardized on this 4-pin connector. So your first round can be extremely easy to get together. You don't have to trace things on a board or run wires or anything with solder. So how are we going to blow through the rest of this? I'm going to present a general workflow that I use when I'm trying to develop a new driver. I'm going to briefly talk about how you might do that on different platforms. I will talk about metadata, how to format what we produce in JSON, and then a little bit of what we would do for later analysis with that. So jumping right into what does I2C look like. I2C is a controller and target network bus, and it shares a clock and data connectors. Plus, there's also a common power and ground. The power doesn't necessarily need to be at the same levels, but typically they are. And the basic operations are that the controller asks for something, and the target responds on the same bus lines. And the targets are listening at all times, and if one is communicating, another one will wait its turn to also use the shared bus. So, some nitty-gritty details here. Mechanical, electrical, and logical. I covered a little bit of the connections there in the previous one. The connectors are just typically copper wire. The target devices, like I said, all share the same wires. Electrically, the voltages for a 0 would be 0 volts, and then 3.3 or 5 are typically the voltages that are run, because those are the typical voltages we see on computers and microcontrollers. Logically, NXP does have a specification for how individual bits are transmitted and what they mean. It's a serialized data protocol, so it is voltage over time is representing individual bits. That's what the clock is doing, is it's helping align when your bits are being interpreted. And the messaging addresses, each target has a specific unique address on the bus. So there is a finite number of addresses that you can use on one bus. And I'll just make a note if anybody gets interested and wants to read something online later. There is a outdated terminology for this arrangement that's true of all computer I/O, which is master and slave is no longer useful. NXP 3 years ago changed the terminology to controller and target. I will use that for the rest of this talk, and I think it's actually more descriptive, amongst other things. So, on to solving a problem. So the driver that we are going to talk about today is a light sensor. I wanted to monitor the light levels in my greenhouse. So first thing I did was a little bit of market research. I'm not going to go through all of the numbers on here, but it's more to demonstrate. I thought about what I wanted, and I made some basic criteria, and then I selected something. I was interested in high accuracy. If I'm going to go to the effort of writing a driver in my spare time, I wanted something that was, worked well, and just needed to work indoors and outdoors. I looked at 4 different websites: SparkFun, Adafruit, DigiKey, and Mouser. SparkFun and Adafruit are companies that make more of these things that you can hold in your hands, like breakout boards. So you're not using tweezers to grab the actual chip that's doing the work. And after considering a few things, the price ranges were actually surprisingly pretty tight between different chips. Their wavelength responses, so I started looking at how these things were specified physically. They were all pretty similar there. The active current, if you wanted to run this on a battery, you should think about how much power it's consuming. And so they all seemed, there was a couple that seemed pretty high, and I moved away from those. So eventually I chose the TSL 2591, which is at the bottom of the list. It's $695 on the breakout board, and it would be less if you bought it on a ribbon and were making the boards yourself. So, having selected our device, the next thing to do, and I should point out, I looked at the data sheets for all of those, and that was another differentiator, as I wanted to find one I could actually understand. So, we will spend a bunch of time in the data sheet in this talk. Data sheets are something provided by every manufacturer, and they're intended to guide the manufacturing and the programming and the integration of that chip into your design. It'll include a lot of things that we'll use, but they also include things like what's the maximum temperature that it can handle, how much voltage or current can it handle, what registers exist, and how big it is, how you'd fit it into a package on the rest of your board design. But the most important thing for what we're talking about today is the register addresses and how to program it. So, this is the page out of the datasheet for the TSL 2591 that lists all of the registers and what they do. So you've got a numerical address, and I should pause here and say that in I2C, addresses both on the bus and in the registers are all noted in hexadecimal, so I will be using that terminology. So the numerical address of the register in the device is listed on this register map, as well as the name of it that they'll use in the documentation, whether it's read, write, or read and write, what it actually does, and then what the reset value is. So when you power on the chip, what its default value is. And some of them are persistent, and some of them aren't. So going down another level, this is still in the data sheet, just looking at register hexadecimal 01, this is a control register. Individual bits inside of this byte have specific uses, and you can access them, and we will go through that a little bit. But just as an overview for this register, Bit 7 is the system reset bit, so you would change that bit if you wanted to reset it to a power on status. 6 does nothing. We shouldn't interact with that. Writing to it doesn't do anything. 5 down to 4 is the analog gain setting for the chip. 3 does nothing in this case, and then 2 down to 0 is the integration time, so how long is it going to collect information before it produces a final number. So, and you'll notice here that it actually lists the gain and time have codes that represent specific states. So if you were to program in binary 001, it would integrate for 200 milliseconds versus 100 at 500 milliseconds. So that's something that eventually I'd want to document when I started using it in the field. So we know what we're going to do. We know what we're going to use. It's time for a little bit of hello sensor and see if we can actually talk to it. So I said a little bit about multi-platform. If you were doing this in Linux, so Raspberry Pi, I use a Raspberry Pi for a lot of development work. On Linux in general, you can use the I2C detect program to list all of the devices on your bus. You can do this on a laptop, server, anything. It's this first graph there is actually from my laptop. And those are 2 internal devices that I was not accessing and not doing anything with. And reading the datasheet, the TSL 2591 has a I2C address of hexadecimal 29. So you'll notice it doesn't show up there, and I did not have it connected to the laptop. On the bottom, MicroPython, there are utility functions that do the same thing. And in this case, I had it plugged into this microcontroller, and it listed hexadecimal 29. So I know that the chip is connected correctly mechanically, electrically, and logically I can in some way contact it on the bus. So I have said hello to it. I've done nothing meaningful with it, but I know that I can move on with programming now that I've physically gotten its attention on the bus. So let's make our first command. This is kind of 3 levels of detail on sending a command on the I2C bus. So our goal is to, on the bus, I should back up a step. I am going to write to read a specific register. So looking at the data sheet, I was looking for a read-only register. And this is part of, I do this regularly with devices. I go look for something that is a read-only register that never changes. And manufacturers include these so that you can do exactly this. During development, I just need to get a constant that I know is supposed to be an exact number, and I know I'm reading things correctly. In this case, it's the identification number, which should be hexadecimal 50. And reading is also the simplest operation that we can do. So what we're going to do is we're going to do a couple of steps. Specifically, the controller is going to write 2 bytes on the bus. First is going to be the I2C address, which is going to be hexadecimal 29, and then a second byte, which is going to tell the target what register I want to access. And that's going to be, in this case, hexadecimal register 12, which is the, I forget the name of it, that's supposed to have the hexadecimal 50 in it. Then the controller will wait, and then it will send a second command, which is a read command, just one 8-bit packet, and then the target will respond on the bus with the 1 byte of the information that it had in hexadecimal register 12, and it should return hexadecimal 50. And then lastly, it's kind of a pseudocode representation of the same thing on the bottom there. So all told, that operation took 4 bytes to do that. So going back to cross-platform a little bit, this is just a little snippet on the left of how CircuitPython, which is, I think, a modern, I don't want to call it a fork, but it's almost a fork of the core MicroPython, how you would read a single byte on the I2C bus. The Linux kernel has its own libraries that do very different things. So if you want to write something very specific for that platform, you will have to write different code. For this talk, I've kind of made a little bit of pseudocode. At the end, I will have a link for a GitHub project of mine that kind of wraps both of these into something a little more standard. But the 3 operations in code are going to be instance an I2C bus class, set a target register on the bus, or I'm sorry, a target address on the bus, and then read or write a register address on the bus at that address. So, using the pseudocode representation, if we make that read register request, and then we use something called a logic analyzer, that's an extra tool that you don't need to do this sort of work, but when you spend enough time on it, it's actually a really valuable thing to have. It's related. It's a similar function, but more specialized to an oscilloscope. It shows electrically what's logically happening on the wires, and it doesn't interfere with the bus. So it just kind of tacks in there, gives you a second view of what you're doing, so you don't just have to debug in code. And so again, the data that we're trying to access is serialized. It's coming in all in a time series, and it's aligned to the clock signal. So what we have here, on the bottom is the clock signal. So that's just pulses that help align the rest of the information. And then on the top is the data line, and that is, we've got our 4 bytes. The controller is sending out, I want address hexadecimal 29, and then which register, hexadecimal 12. And then the second command there, it's saying, okay, now I want to read that value at hexadecimal 29, and then the target responds with the value of that register, hexadecimal 50. And all told, that took roughly 0.4 milliseconds, according to the clock there. And then in the middle here, this is the actual voltages that we're seeing. This is the digitized representation, but the actual high sample rate, you don't capture that actually on the I2C bus. That's what the logic analyzer is doing. But you can see that it's not perfect square waveforms. There's no such thing. So we've been able to read 1 register. We've got a few more to do. What I would do now is I would go back to the register table, and I would kind of set some priorities of increasing complexity, and at each step I'm kind of validating that things are working and I should commit more effort into adding another feature. So I've kind of highlighted here on the table a few of the other things that I want to do. First would be device status, because that's a read-only register as well, and that's at address 13. And then I would tackle register 0 and hexadecimal 1. Those are read-write registers, and those have individual fields inside of that byte that we're going to be interested in. That was the one that we looked at in more detail earlier. And then lastly, I would do the read register, the data read registers, hexadecimal 13 through 17. And you'll notice there's a bunch that I didn't highlight, and I'm not going to do anything with those. So deciding what features you want to implement really helps scope the project to something doable. I don't really want to use these interrupt features. Interrupts are something that a lot of chips have, where you can put most of your device to a sleep mode, and when a certain threshold event happens, it sends an electrical signal out on a pin. So you get an electrical signal, not a software signal, that could then wake up another device. So say this light sensor could decide to send out an interrupt when the lights come on in the room, and now you power on the rest of your board and take some action, and you were in a sleep state, saving your power until then. But I'm interested in collecting data with this device, so I'm going to skip all of those registers and programming those. So reading and writing to the control register. This is the same operation as we did before, reading the entire 8 bits and then doing some bitwise operations to pull out the individual fields, just shifting, masking, and adding. And then to do the reverse is to create the entire 8 bits is to just do the reverse. A second command that this is, again, a generalized version of what you would use, but writing that byte out to the register address hexadecimal 01, the target will know what to do with it, and we'll write that entire 8 bits into that register. The next thing I would do is I would read it again and make sure that change happened. So I'd actually do a loop back on myself logically. So last thing is reading the data registers, and these were read registers, so it's really just doing what we have first implemented, but on something that actually has meaningful information. So 2 things, you're going to do a bit shift on it. I think it's interesting to look at how long that took. This whole sequence took 4.5 milliseconds, and just shifting it. These are 16-bit values, so this is where reading the datasheet matters, is that it actually is storing that 16 bits in 2 registers, and you have to do the math off chip. So now we have 2 channels of data, and what are we going to do with them? And this is, I keep saying this, and I will keep saying this, we're back to the datasheet. So what is the channel 0, 16 bits of data that we got? That is the broadband radiation that the sensor received, and channel 1 is infrared. And in a separate design document, so manufacturers will create the datasheet, which will tell you how to program and engineer the device. They will also make a lot of things called application notes, or this company called the design notes, that will tell you how to use the device meaningfully. And so in a totally separate document, they described a lot of light detection concepts. It was very well written. Oftentimes these companies are, you're reading documents by experts in a very, very specific field. They're very interesting to read, just as a, maybe not light bedtime reading, but this chart came out of the application note, and I had never really thought about the fact that the green line there is our eye's response to specific wavelengths of light. We are more attuned to certain wavelengths of light, and we see them brighter than others. And the silicone on this chip has the waveform response of the black and the red. So if I want to decide, like, is it bright in the room and turn the lights down, the sensor is going to see one thing, the human eye is going to see something else. And this goes into a whole other thing. You can look at, like, animals have different sorts of wavelength responses due to evolution and all sorts of things. So this is goes a lot of places besides this talk. But they also provided this equation to calibrate this, and I just used a free app on my phone. I didn't feel like buying a calibrated lux meter for this project, but I collected a few lux measurements with my phone, and then I collected a few pieces of data with the chip, applied this equation, and I got a lux number out. They provide this and they don't build it in because if you put a sensor like this behind some sort of glass, you'll change the way it's collecting information and you want to calibrate it yourself. So some chips will come pre-calibrated and it's good enough. This, because of every application was going to bias it so much, the company chose to basically force the users to do some sort of calibration themselves in application. So we have some data, and I love analyzing data, so this is where we get into data sciencey stuff. Where was the metadata? Let's make some metadata. So I wrote a class to hold things that I thought were relevant to somebody that would end up with this later. There's the URL, where I also found the design document. What were we measuring originally? Were ADC counts. They were integer value ADC counts, and then when we ran it through the equation, it became a floating point lux value. So we add that in there. Sometimes the precision and accuracy is relevant. Sometimes they don't exactly describe it because it's calibration specific, but I tried my best. And then I added those constants over there are from the equation. So if I did want to recreate the equation later, I could see when I collected this data, what constants did I use to compute the lux value. So outputting this, everybody loves JSON. I love JSON. Taking the values from the class that's holding the driver and the methods, just outputting it into JSON. And I have a lot to say about timestamps, but it's got a timestamp on it and where it came from. And if you just put that in a file or feed it into pandas, I mean, it's important to one line to read it when you format it in JSON. You are making less work for yourself down the road. And you're making it, you're putting some data engineers potentially out of work too, because JSON can just be like new line delimited, directly ingested into every cloud platform's data warehouse at this point. So when I first started programming these for context, I think the YPy, I probably couldn't fit more than 3 of these overly verbose files that I was writing. The entire project I have now fits in like 1/8 of one of these things in the onboard memory. So there's not a lot of resources that are being taken up by creating small amounts of JSON and saving them to an SD card or transmitting them at this point. And it saves a lot of downstream ETL, I think, if you use Python. And what I've got here in the middle is injecting the metadata at regular intervals into that. And again, the cloud database systems will just add extra null-filled columns for those extra keys that they find in the JSON. So you don't have to go and selectively parse the JSON in a separate compute engine instance. It just does it automatically. It's probably consuming compute cycles in BigQuery to do that, but I think, actually I don't know. I'm not good with the cloud billing on that. Okay, and that's it. I've got a framework that I've been building for various projects of my own. If anybody has any uses or features that are interested in it or want to contribute, I would love to talk to you about it. Another user on GitHub maintains a really cool list called Awesome MicroPython. A lot of people have written drivers. There are a lot of really cool devices out there that are very obscure or very new that there are not drivers for. So that's the point of this talk, is I hope that everybody feels like they could go write a driver or start on it. It would be great to have more of these in the ecosystem so that people can just pull them off the shelf and build new things with them. So with that, I think I'm done. Thank you.